What would happen if you fell into a black hole? Would you see eternity unfold in a second, or nothing at all? Would time stop, or would you? A black hole is not just a region of space. It is a cosmic tyrant where gravity becomes so intense that nothing, not matter, not energy, not even light, can escape. It is the ultimate boundary, a tear in the fabric of space-time. And if you were ever unlucky or perhaps curious enough to fall in, your journey would challenge every law of physics we know. You are about to become a messenger of the cosmos, delivering information to a place it can never return from. This is the ultimate cosmic thought experiment. What happens when you cross the point of no return? Welcome to Cosmic Crunch. Get ready for the ultimate fall. Anatomy of a cosmic tyrant, the birth of a black hole. A black hole begins its life, like many cosmic tragedies do, in the violent death of a star. When a star at least 20 times more massive than our Sun runs out of nuclear fuel, it can no longer push outward against its own tremendous gravity. The core collapses, compressing millions of kilometers of gas into something smaller than a city. The collapse is unstoppable. Electrons and protons merge into neutrons, then even those are crushed beyond recognition. The star's outer layers explode as a brilliant supernova, while the core implodes into the center, a point of infinite density called the singularity. The boundary of no return, event horizons. Every black hole has three defining features: the singularity, the dense, infinitely small core where space and time cease to exist as we know them; the event horizon, the invisible boundary surrounding the singularity. It's the critical distance where the escape velocity exactly equals the speed of light. Cross that line, and you are gone from the universe's perspective forever. The ergosphere and frame, dragging. If the black hole is spinning, which most are, it adds another region called the ergosphere. The black hole's rotation is so immense that it drags space-time around with it, forcing anything within the ergosphere to rotate as well. This effect, called frame dragging, means you could theoretically lower an energy-generating device into the ergosphere, spin it, and pull energy out, making it an alien power source. The observer's paradox, time and light. The visual descent, gravitational lensing. Let's imagine you're an astronaut orbiting a supermassive black hole. As you fall closer, the extreme gravity begins to warp light from the entire universe. This is gravitational lensing. Stars bend into a bright halo around the black disk. The black hole doesn't look like a simple hole. It looks like a sphere of shimmering fire, wrapped in darkness. Half the sky above you appears to compress into a small, bright window. The stars behind the black hole become visible, stretched like smears of paint across the darkness. It is the ultimate celestial funhouse mirror. Einstein's time dilation. The most mind-bending effect is time dilation. From the perspective of your shipmates watching safely from afar, two things happen to you as you approach the horizon. Slowing down. Your descent appears to slow down drastically, approaching zero speed. Redshifting. The light waves coming from your suit and flashlight get stretched by the powerful gravity, fading to red, then infrared, and finally vanishing entirely as they cross the radio spectrum. To your shipmates, time for you appears to freeze right at the event horizon. Your final image becomes a fixed, ghost-like apparition, never actually crossing the boundary, forever frozen in the final moment of the universe's time. But from your own perspective, the one doing the falling, you notice none of this. Your wristwatch, your heart rate, and your perception of time all feel completely normal. You cross the horizon without noticing it. This is Einstein's relativity at its most bizarre, allowing both realities to be true. Spaghettification and the cosmic shredder. The tidal force, the cosmic noodle. Now comes the infamous visceral part, spaghettification. Gravity near a black hole is not uniform. The pull on the atom closest to the singularity, say your foot, is astronomically stronger than the pull on the atom furthest away, your head. This differential force is known as the tidal force, and it grows exponentially as you get closer. The tidal forces stretch you violently along the direction of the fall while simultaneously compressing you sideways, tearing molecular bonds and turning you, atom by atom, into a stream of superheated cosmic plasma, or a noodle. Big hole versus small hole. Your survival time depends entirely on the black hole's size. Stellar mass black hole. These are small, only about 10 kilometers wide. Because the singularity is so close to the horizon, the tidal forces are extreme even far outside the event horizon. Spaghettification happens instantly and violently, long before you reach the point of no return. You'd be shredded and vaporized into a stream of particles. Supermassive black hole, like the one at the center of our galaxy, Sagittarius A star. These are millions or billions of times the mass of the Sun. Their event horizons are huge, millions of kilometers wide. Because the gradient of gravity is spread out over a massive distance, the tidal forces are mild until you're deep inside. You might cross the event horizon intact, experiencing a moment of profound, normal-feeling terror before physics breaks you apart inside. The ultimate prison. As you pass the horizon, your speed must exceed the speed of light to escape. You are moving faster than the universe's speed limit relative to the outside world, yet you feel like you are standing still. This is the ultimate prison, one where the exit sign is always receding at light speed, and the only path forward is inward. The view from inside and the information paradox. Space and time swap roles. Once past the horizon, the reality you know is fundamentally inverted. Space and time switch roles. In our normal universe, you can move freely in space, but only forward in time. Inside the event horizon, you can move freely in time, but you are forced irresistibly inward in space. For you, the singularity is no longer a place. It is a moment in your future that you are guaranteed to reach, just as guaranteed as you are to reach tomorrow. Every path leads inward. The final light show. Light from the outside universe can still reach you for a time. But as you fall toward the singularity, this light is infinitely blue-shifted and amplified. The entire history of the universe, billions of years of cosmic evolution, gets compressed and sped up. You might witness stars forming, galaxies aging, and the final fade of the universe in mere milliseconds before the radiation intensity becomes lethal and the singularity fills your vision. The black hole information paradox. This is where the physics truly breaks. General relativity dictates that a black hole is defined only by its mass, charge, and angular momentum. It has no memory of the matter that fell in. Yet, quantum mechanics insists that information must be conserved. This is the black hole information paradox. If information can't return from the black hole, and yet all quantum information must be conserved, what happens to the knowledge of you? Every atom, every memory, every unique quantum state? Does it vanish? The paradox suggests that information might never truly be lost, but where does it go? This puzzle is at the core of unifying all of physics. Beyond the singularity, theories of what's next. The ultimate question, what lies on the other side of the singularity? General relativity offers a mathematical answer, but physics offers several fascinating speculations. The white hole hypothesis. A white hole is the exact mathematical reverse of a black hole, a region that can only expel matter, not absorb it. Some theorists speculate that the singularity acts as a valve, routing matter falling into a black hole in one universe to emerge from a white hole somewhere else, perhaps in an entirely separate region of space-time, or even a completely separate universe. the wormhole and the bridge. Einstein's equations of relativity allow for Einstein-Rosen bridges, better known as wormholes, connecting two distant points in space-time. Theoretically, the singularity could be a mouth to such a bridge. Falling into one mouth might eject you from another, though again, the immense tidal forces and intense radiation would almost certainly destroy you first. The wormhole would likely collapse faster than you could pass through it. The quantum bounce and baby universes. Some modern quantum gravity theories, like loop quantum gravity, propose that when matter collapses past a critical density, it rebounds. It bounces, creating a new expanding universe on the other side. This is an elegant solution to the singularity problem. Singularities don't exist. They are simply the bounce point for a new cosmos. If this is true, every black hole could be a cosmic seed, giving birth to new realities. And somewhere inside another universe's black hole, ours might have begun the very same way. The science of falling, evidence and paradox. Hawking radiation and the black hole's decay. Black holes aren't perfectly black. Stephen Hawking proved that quantum effects near the event horizon cause black holes to slowly leak energy in the form of Hawking radiation. This is incredibly slow, but it means black holes eventually evaporate. A small stellar mass black hole could take 10 to the 67th power years to fully vanish. This evaporation process is central to the information paradox. What happens to the information in the last burst of radiation? The firewall paradox. For decades, Einstein's general relativity predicted smooth space-time all the way down to the singularity. But quantum physics suggests a contradiction. A violent firewall of high-energy particles right at the event horizon that would instantly vaporize anything that attempts to cross. This contradiction is at the heart of modern physics. It's not just about black holes. It's about finding the long-sought theory of everything that unites the rules of the cosmos with the rules of the quantum world. Our evidence. We have hard proof that these cosmic tyrants exist. The Event Horizon Telescope's stunning photograph of the black hole in M87, showing the glowing ring of light being warped around the shadow. The detection of gravitational waves by the LIGO Observatory, which are ripples in space-time caused by colliding black holes. The rapid eccentric orbits of stars around the invisible 4 million solar mass object at the center of our own galaxy. Sagittarius, a star. Every equation, every simulation, every telescope image brings us one step closer to the truth of the ultimate fall. If you ever did fall into a black hole, you wouldn't survive, but your journey would be unforgettable in the most literal sense. Time would slow. The universe would stretch. You would see infinity compressed into a moment. And then nothing. Black holes are where the known universe ends and the unknown begins. Nature's reminder that even in an age of science, mystery still rules the stars. And perhaps somewhere beyond the singularity, the universe itself is watching you fall. If this journey through the mouth of a black hole pulled you in, hit that like button and subscribe to Cosmic Crunch, where we dive into the wildest, darkest, and strangest corners of the universe. Drop a comment below. Would you take the plunge, knowing what waits beyond?